Welcome for you chemistry students. So in your first lesson on thermochemistry, you were asked to go over some terms and do definitions. So today I want to review a few of those and sort of pull them together. And then we're going to do some calculations on enthalpy. So first of all, the process of measuring energy changes in a chemical system is calorimetry, and the device that we use is called a calorimeter to do that. In the lab, had we been able to do a lab, we would have been using literally a styrofoam coffee cup calorimeter, which would be 2 coffee cups with then a lid with a third cup on top. There are very expensive calorimeters that are way more insulating than our coffee cup version. But either way, we assume that a calorimeter is isolated. And isolated means that neither matter can enter or leave or energy. So we do make an assumption that we are not losing energy or gaining energy from outside of the calorimeter. So because we're assuming that, we are saying that calorimetry is allowing the law of conservation of energy to be obeyed. And because of that the chemicals that are either possibly gaining or losing heat, where that has to be happening from is the surroundings, but strictly the surroundings within the calorimeter, which is going to be water, or it could be a solution. Because a lot of chemical reactions that we do, as you know, we mix a solution of them, and then that solution can react with another solution. So either way, it's going to be aqueous. And because it's aqueous, we also sort of make an assumption that it acts like water, even though there might be other chemicals dissolved in it. And that will become important later when we're doing some calculations. All right, so chemical systems, which is really what we're just calling our substance that we're talking about, and that substance might be about to undergo a chemical change, or it might be doing a physical change, like a change of state. But either way, the substances are going to have 2 types of energy, which you reviewed yesterday. So kinetic is motion. It's motion of its atoms and molecules, and that can be rotational, translational, or vibrational. And then, of course, there's potential energy, which is really contained within the atoms. So potential energy of an atom is why we have nuclear energy, for example. And then the bonds, because when you make and break bonds, you can release or gain energy. So between the kinetic and the potential, all that energy adds up into something that we're going to call enthalpy. And we would like to know the value of that enthalpy. However, it is hard to measure. But what we can measure is how that enthalpy value changes after our system undergoes some type of a change. So we basically have to compare the enthalpy of the reactants to the enthalpy of the products, and then we can look at that difference, because otherwise it's very hard for us to measure the energy that is, contained in an atom or a bond, for example. So enthalpy change, we're going to call delta H. All right, so this whole idea of using a calorimeter to come up with enthalpy changes is based on, again, the law of conservation of energy, which states that the delta H, or enthalpy change of your system, your chemicals, has to be equal to the heat that is either gained or lost by the surroundings. And again, the surroundings in an ideal calorimeter is strictly going to be the water environment that your dissolved chemicals are reacting in, or perhaps you're just dissolving a chemical, because when things dissolve, they can also be exothermic or endothermic. And I should mention too that one reaction we study a lot is combustion. And a combustion calorimeter is much different. It's designed to actually burn a substance inside of it, so clearly we don't have a water environment. We won't be doing any calculations with a combustion type of calorimeter. Okay, so throughout a reaction, or what we call the reaction progress, the total energy of your system is going to be constant, because energy can't be created and destroyed, but energy can definitely be changed. So you've got this mixture of potential energy and some motion or kinetic energy. And as you put your system through a change, which again might be chemical, more than likely in this class, but it could be a change of state, physical, it could be dissolving, which is physical, could be nuclear. What's going to happen is the total energy has to stay constant. So you'll see here in pink, I have the potential energy, and as this particular system is progressing, it is decreasing. But that means that the kinetic must be increasing. And if you were to, add up the two values, this is not a very scientific graph, but anywhere you would add those up, you should get the same total energy. So you have, a big value of potential, a little value of kinetic, you're going to get a certain value. Here you've got kind of like a medium of both. They should always add up to the same value because the energy is going to be constant. Okay, so just kind of referring to that diagram, just a couple things to think about. So if your potential energy is decreasing, which is what I've put in this diagram, because going forward, potential energy diagrams are usually all you see. So I just had a general energy diagram, but usually you'll see potential energy. So you'll be able to see whether potential energy is decreasing or potential energy could be increasing. But in this case, it's decreasing. So my question is, what does that mean about the kinetic energy? Well, obviously, the kinetic absolutely has to be increasing because our total energy is going to be constant. Now, if your motion energy or kinetic energy is increasing, what type of reaction do we have? And your choice is exothermic or endothermic. And when you have more motion of molecules, that is when you're going to feel an increase in temperature. So this type of reaction would be exothermic, because it is going to be releasing heat, and you would feel that in the form, well, you would feel it because it has more kinetic energy. Okay, so that is enthalpy change, and now this is a brand new term that you did not look at all yesterday, and that is molar enthalpy. Now, you're definitely familiar with moles from grade 11 chemistry. And so now we're basically just saying, okay, so we have these enthalpy changes when a reaction happens, but let's quantify that for one particular substance of that reaction, and we'll talk about 1 mole of that substance. So again, it doesn't necessarily have to be a chemical reaction. It could be a physical change. So it could be things like melting, freezing, evaporating, chemical reactions, or nuclear changes as well. So in general, we just tend to say, whatever kind of change we're talking about, we're just going to call it X, and then you fill that in when you actually know what type of change we're looking at. So just as an example, if our change is going to be a combustion reaction, so the combustion of methane, so methane plus oxygen obviously is required for combustion. Here's our products. So over here, I have molar enthalpy of combustion of methane. So notice instead of an X, now we have combustion, and I've even said of what, because it's going to make a difference what fuel you're burning, what the molar enthalpy value will be. Now this value here could be found on your textbook on page 799, or on any chart that you may Google if you're looking up molar enthalpies. So Um, no, the one thing I do want to point out is because it's a molar enthalpy and it's for methane, this value here has to be for 1 mole. And obviously this equation is balanced, and it does happen to work out that methane is 1 mole when you balance it. But you'll sometimes see in your textbook when you're doing some problems that occasionally you'll see a reaction wrote out and afterwards you'll have a molar enthalpy, and the reaction will have things like 1/2 or 3/2 when it's balanced, which, you know, in grade 10 and 11, that was a big no-no. You weren't allowed to use fractions to balance things. But in this case, it's absolutely necessary that the substance that you're getting your value for the molar enthalpy, it has to be 1 mole. So if that means you get some funny fractions, then so be it. Okay, just a reminder, because this is something you'll never want to get confused, is that once again, exothermic reactions are going to have a negative value for their enthalpy. But in this case, now it's a molar enthalpy. So no different than what you looked at yesterday when you were doing your definitions. And exothermic is, of course, positive. So exothermic, remember, means your system is going to release heat, and therefore, if it's a chemical reaction, for example, it's going to feel warmer. And endothermic reactions actually take in heat or absorb heat, and therefore, as a result, those surroundings end up feeling cold. So we use, injury packs in both of these situations. You can have an exothermic reaction that makes a nice little hot pad when you mix the chemicals, but then you can also make a nice ice pack by doing an endothermic reaction. Okay, so when you have a change, clearly the amount of energy involved is going to be much greater if you have more of your actual chemicals, for example, or your system. So the number of moles is going to affect your overall enthalpy change of your reaction. So this is the first little formula for calculations today. And basically, it's just saying the enthalpy change of the reaction, and this value here could be in joules, but it's probably going to be in kilojoules. But it wouldn't be wrong to be in joules. It's just that when you look up your molar enthalpy off of a chart, it's usually in kilojoules per mole. And they have to match. You can't have your enthalpy change in joules and your molar enthalpy in kilojoules. So if they're not matched, you're going to have to either multiply or divide something by 1,000 to get that. Okay, now I'm just going to put in brackets here that you're going to get this value from a chart unless I've given it to you in a question. And then N is your number of moles. Now, lots of times questions aren't going to give you the number of moles. They're going to give you a mass, but that's okay, because if you have a mass, you can use the molar mass and end up getting the number of moles. But similarly, you might be asked to even solve for a mass. So at first you're going to solve for the moles, and then you can solve for the mass using the molar mass. We will review that grade 11 stuff right now. Okay, so here's an example. So as I said, we're predominantly going to be looking at chemical reactions, but there are some physical changes that we're going to look at as well. And this is an example right here. When you dissolve a salt in water, that is just a physical change. You're really not making anything new. And as I mentioned, there are lots of salts that when you dissolve them in water, you can actually noticeably detect that the temperature of your solution is either warmer or colder after you've dissolved it. And, sometimes it's not noticeable, but it does happen quite often when you dissolve something that you're going to either have a gain or a loss of heat. So we're going to dissolve 5 grams of a salt, potassium chloride, in water, and we're wondering what is the enthalpy change. And you can look up on a chart, or I've given it to you here, that the molar enthalpy of solution for potassium chloride is positive, because it's endothermic, so 17.2 kilojoules per mole. So just to kind of get organized here, it asks for the enthalpy change. So that is just delta H, okay? They gave us the molar enthalpy of solution. So these are different. Notice our delta H was kilojoules and our delta HX, or molar enthalpy, was in kilojoules per mole. So this, we're actually going to replace the X and we're going to put solution and we're going to put KCl. That's not very neat. There we go. And that was given, and it was positive 17.2 kilojoules per mole. Now, otherwise, so if we look up here, we're doing well. We've got 2 things, and we could solve for moles, I guess, but we have grams. So we have a mass. Okay, now, just to recall from grade 11, if you have a mass and you want moles, you need to multiply it by the molar mass, and you need to put the unit on the bottom that you're starting with. So we're starting with grams, so we want the grams on the bottom. We want the molar mass of 1 mole of potassium chloride on the top. And I'm not going to actually show the work for this, but you're going to add up 1 potassium, which is 39.10, and you're going to add 1 chlorine, 35.45, and you are going to get 74.55 grams. So now grams will cancel, and the answer for our moles is going to be 0.067, and I believe the next number was a 0. I only want 2 sig digs. I've got 4 in my molar mass. I've got 2 from my question, so that's all I want. And that is moles of potassium chloride, and that is N. So now I've got N, I've got my molar enthalpy, so now I'm just going to plug it in. So 0.067 moles times a positive 17.2 kilojoules per mole. Actually, you know what? I'm going to write that differently, just to be more like how we always did it in grade 11. So my kilojoules on top, my 1 mole on the bottom. Okay, just so we remember that they cancel out. And comes out to 1.15, but once again, we're only allowed 2 sig digs. So 1.2 unit is kilojoules, and that is our enthalpy change during this, dissolving of this salt. Now, because our answer is positive, and we definitely should put the positive sign, even though you kind of assume it's positive if there's no negative, that is telling us that this is endothermic, and this solution would actually feel a little bit colder because this process of dissolving would have taken some energy. Okay, so it took energy from the water, and therefore it's going to feel colder. Okay, so now we're just going to really push a bunch of formulas together. So we've been talking about, the fact that where the energy comes from for a system to do a change has to be from the surroundings. So we talked about this relationship here. Enthalpy change of your system is the heat of your surroundings, plus or minus. Yesterday you looked at and practiced using the formula for heat, which is mass times specific heat capacity times temperature change. So if we take our new formula for enthalpy change, which is that, moles times molar enthalpy, and then if we take our formula that we had for heat right here and plug it in there, we can make another brand new big formula that is really just two formulas that you have now seen. Now this side here is going to be what we call the system, because it's going to have some type of substance that has a molar, molar enthalpy of combustion or molar enthalpy of solution or of neutralization or whatever. Okay, and this is going to be the surroundings or the environment. Okay, and they have to be equal because we said that's where the heat comes from or goes to, is the surroundings. Okay, all right, so we could use this type of formula for a calorimeter where if, for example, this could be the solution in a calorimeter. So it would be water, probably, or even if it's a solution, you assume it's water-based, that it's aqueous. So you'd need to know the mass of it, the specific heat capacity of water, which we can look up, and then the temperature change of the water in your calorimeter. And then all of that would have to be equal to, what happened with the system, how much, and what the molar enthalpy of that reaction was. Now, on a much larger scale, which is definitely not a calorimeter, it's the exact same thing going on when you have a hot water tank, which you may at home, that is being heated by propane. So the combustion of propane specifically. So if propane gas undergoes combustion to heat a tank of water, so that's kind of like we've got a reaction, and then we've got our water, which is a very large calorimeter, I guess. And then I've given you various pieces of information, like how much water's in your tank, how much are you heating the water up by, and then the question is, how much propane do you actually need to do that? So how we want to set this up is we want to say the system has to equal the surroundings. Okay, and in this case, the system is the propane and the surroundings is the water tank. Okay, so now let's plug in our little formula here. And I'm going to put combustion, and propane is C3H8, which all of you guys know from organic chemistry, MC delta T. Okay. Now, I would highly suggest always setting up a question like this, and then literally keeping your various pieces of information organized on both sides of this equation, and then eventually you'll actually solve the equation. So anything to do with the water needs to go over here. Anything to do with the propane is going to go over here. So first of all, we're asked for the mass of the propane. So I'm just going to write here mass equals, because I know that's what I'm trying to get eventually. Okay. Now, in this formula, I have N, which is moles. So I'm going to have to figure out the molar mass of propane, which we can do that right now. So molar mass of C3H8 is going to be 44.11 grams per mole. So it's 3 carbons and 8 hydrogens added up. Okay. And the other thing I know over here, or can look up, is the molar enthalpy of combustion for propane, which I'm just going to leave that blank. Oh no, I guess I better put it here. So C3H8. And that I'm going to have to find on a chart. And, oops, sorry. 2,220 kilojoules per mole. And if you look, that is on page 799 of your textbook. Okay. So that is everything I know and can figure out about propane for now. So now let's go over here to water. 200 liters. So they've given me a volume of 200 liters. I have nothing up here that is to do with a volume, but that's okay because I can use a conversion factor and say 1 kilogram of water is going to take up 1 liter, or vice versa. 1 liter weighs 1 kilogram because the density of water is a gram per mil or a kilogram per liter. So I really do have 200 kilograms, which is going to be my mass. So now I've got my mass. Specific heat capacity of water is also on a chart somewhere in your book, but I just kind of forget which page it's on right now, but you can always look it up. It's 4.18. And the thing with specific heat capacities, which you may have noticed yesterday, is they can be in joules per gram degrees Celsius, or they can be in kilojoules per kilogram degrees Celsius. And the number stays the same because like it's just a factor of 1,000 over top of a factor of 1,000, or a factor of 1 over top of a factor of 1, so it makes no difference. The key is though, you'll want to make sure you choose which one to write to kind of match other data that you have in your question. That is what's very important. Okay, so I'm just going to put a little arrow here and just say must match. Okay. Change in temperature. We're going to take the final temperature, which is 65 degrees, subtract what it started off at, and we have 45 degrees. Okay. So at this point, we're going to do a little bit of formula rearranging, because this question is asking for mass. I'm just going to squeeze in here that we're going to need moles. And then once we know moles, we can always get to mass. So we have everything that we need here. We've got the molar enthalpy of combustion, the mass, specific heat capacity, the temperature. If we solve for moles, then we can get to mass. So to rearrange this equation, we're going to have moles. Everything on this side stays the same. We're trying to figure out how do we get rid of that. We're going to have to divide it out of the other side because we're dividing it out of both sides. Okay. So now we'll plug in our numbers. So we've got 200 kilograms. Oh, and I guess the other thing is I could just make a little arrow here just to show kilograms matched, kilojoules matched. So everything has to be lined up. And that's going to be times 4.18 kilojoules per kilogram degrees Celsius. And then finally times 45 degrees Celsius. And then you can see that a lot of these things are going to cancel. Like kilograms is going to cancel with kilograms on the bottom. Celsius is on the bottom. That will cancel with that Celsius. So now we've got kilojoules on the top. But on the bottom, we're now going to put 2,220 kilojoules per mole. And if you invert and multiply, those kilojoules will cancel, and your final answer will be in moles, which is totally what you expected, being as we're solving for moles. And if you do this on your calculator, you should get 16.95 or thereabouts. I would not clear your calculator at this point. I'm just writing this down. So this is how much propane we have. And then we already figured out the molar mass so that we would be able to get it into grams or kilograms, or no, it's going to be in grams. So 44.11 grams. Moles are going to cancel. And mass is going to end up being 747.4 grams. But if we look back at all the data you were given, everything was 3 sig digs. Molar mass was 4, so you're allowed 3. And there's your final answer. Okay, that was a lot of information for one day. So obviously you'll need to practice some of these questions, and we'll see you next time. Thank you.